So let's take a look at how these flags affect the, uh, the commands, or how the commands and the numbers that they're operating on set these flags. So we'll start with the add LW instruction and look at the status register. We'll start by looking at the flag bits C, DC, and Z, our carry, digital carry, and Z flags. Some examples will probably help you to get an idea here, so we'll look at about 3 examples. Although the flag bits C, Z, DC, OV, and N are affected by the add LW instruction, we'll focus on just these 3 to start with. We'll just kind of wade our way in. The other flag bits will be discussed later because they relate only to signed number operations. So we've got 3 examples we'll take a look at. Some instructions are not affected. Some instructions affect all 5 flags, C, DC, Z, OV, and N, but some instructions affect no flags at all. And we'll see a table later of some of these instructions, these commands, and you'll see some of them are not affected. The move instructions are one category, except the move F. Some instructions affect only the Z or the N flag bits, or both. The logic instructions then are in this category. So let's start by pulling up an example here. In this example, we're asked to show the status of the bits of the flags C, DC, and Z after the addition of 38 hex and 2F hex in the following instructions. So we're going to do a move LW 38 hex. So that will move 38 into the working register. And to that, we are going to add a literal value and add it right into the working register, 2F. Okay, so 2F to the working register. So if we look at the solution, in hex, we have 38 hex plus 2F hex, and the sum of those two give us a 67, which is fine. You can go through your calculations and solve this. 8 plus F gives us a 23, so we have to do that rule of subtracting 16 from it, and we get a 7. And then we have a carry in doing so, so 1 plus 3 plus 2 gives us a 6, so a 67. But because we're dealing with 8-bit words here, it really makes more sense to look at it in the binary sense. That way we've got an idea what's happening from D0 to D7 as we add each of these values together. So as you can see here, when we add those two values together as an 8-bit value, we end up with a 01100111, which gives us that 67 hex, which is stored then in the working register. So let's look at how the bits, the flags on this are affected by this addition. First off, we have a carry equal to 0, because remember what our rules said for a carry. The flag is set whenever there is a carry out from the D7 bit. This flag bit is affected then by 8-bit addition or subtraction. So we have a 0 because there's no carry beyond the D7. The next one says for the digital carry, we have a 1 because there is a carry from D3 to D4. So if the instructions told us if there is a carry from D3 to D4 during the add or subtraction, this bit is set. Otherwise, it's clear. This flag bit is used by instructions to perform binary coded decimal arithmetic. And then finally, we have Z equal to 0 because the working register has a value other than 0 after the addition. Well, of course it does. It has 67 hex setting there. So with that Z flag, the 0 flag reflects the addition of an arithmetic or logic operation. If the result is 0, then Z is equal to 1. If it's equal to 0, if the Z is equal to 0, then the result is not 0. So the result here is not 0. So that's our first example here of adding those two hex values together and looking to see what the flag bits are doing afterwards. The next example says show the status of the C, DC, and Z flags after the addition of 9C in hex to 64H in hex. So again, we use a move literal to move 9C into the working register, and then we add 64H literally to that value in the working register. Again, the solution shows the hex solution to that. You can add the hex solution values together. C plus 4 gives us a value of 0 because we have 16. You subtract 16 from it, you have 0 left. And then the second one is also 16, 9 plus 6, which gives us a 1 and a 0, 0 with a carry of 1. But if we look at this in the binary sense, it becomes very, very evident. We have all zeros as the answer. The working register has 0 stored in it. So as we go through and look at each of the flags, C equals 1 in this case because there is a carry beyond the D7 bit. Okay. DC is a 1 because there is a carry from the D3 to the D4 bit. And then finally Z equals 1 because the working register has a value of 0. We're going through this stuff, writing these simple commands in assembly language. Later we're going to see, when we look at this in the piece of software called MP Lab, that you are actually going to see these flags set when we go into the software. But right now we just need to get you on board with a conceptual idea of writing the code and using the rules to come up with what we think are the answers. The last one, we're going to show the status of those same 3 flags, C, DC, and Z, after the addition of an 88 hex to 93 hex. So again, literal move into the working register, 88 hex, add a value, literally 93 hex to that 88, and we end up with a value in the working register. So if we take it apart, 8 and 8, 9 and 3, add them together using the binary, we can see our 8-bit values here. We end up with something other than 0 in the working register, which relates to a value of, that should be 11 and not 1. I'll have to correct that. Anyway, so again, if we look at the characteristics of the flag, C equals 1 because there is a carry beyond the D7. DC equals 0 because there is no carry from 3 to 4. And 0 because the working register has a value other than 0 after the addition. This table shows us then the commands, the instructions that have flags associated with them. In this case, we can see, again, we haven't been introduced to a lot of these other than the top few, but you get an idea from this how many instructions, how many actually have the flag bits that will be set given a logic or an arithmetic value associated with it. So that is adding and looking at the flag bits associated with doing the operations.